So logarithmic differentiation is the process where instead of taking the derivative like you normally would with product rules and quotient rules, you first take the natural log of both sides, because you have log laws that let you break things up. Then you can do implicit differentiation, and sometimes this makes overly complicated derivatives easier to do. So we'll look at examples. Like, do you see that you would have, if you did this normally, do you see that you would have a quotient rule? And in your numerator, you would have a product rule. And in your denominator, you have a chain rule. And in one of the things in your numerator, you have another product rule. So yes, we could do this by just doing all the rules we have so far, and that would be fine. I think I did one up on the board like a while back, that was super long. You could do this one super long as well. But what we could do is we could take the natural log of both sides. Because you have log laws for dividing, log laws for multiplying, and log laws for exponents. And using those log laws might take away some of your chain rule, some of your quotient rule items. So I take the natural log of both sides, and then on the right side, I start playing with my log laws. Now, first of all, whatever's multiplied in your numerator will always be added. Slide that one down. Whatever's in your denominator, even if you have multiple things multiplied, those will always be subtracted. So I have two things that are added and two things that are subtracted. And then if you have exponents to the whole thing inside of a natural log, you could bring that 4 out in front, and with the square root, you could bring the 1/2 out in front. So by applying the natural log of both sides, we went from the original having quotient rule, product rule inside of quotient rule, and two chain rules inside of that, doable but complicated. We now have implicit differentiation with just chain rules. That's the only thing that's in those natural logs. So hopefully this is a little bit easier. If we take the derivative of each thing, it's a little bit easier. Because even pulling those powers out in front, now they're just coefficients. So we do the derivative of each one. The derivative of natural log of a y would be 1 over y dy dx. The black there is your chain rule. The derivative of natural log would be 1 over, keep the inside the same, multiply by the derivative of the inside. So each of these are little chain rules. Natural log, derivative of the outside function would be 1 over, keep the inside the same, multiply by the derivative of the inside. And the last one, 1 over, keep the inside the same, multiply by the derivative of the inside. Now you wanted to find the derivative. That's your dy dx. So if I want to find my derivative, all I would need to do is multiply both sides by y. I'm going to keep that right-hand side in brackets. And then, since I knew what y was originally, yes?
Where did the half go?
Did it just disappear on us?
Yeah.
Yeah, okay, it should still be there. It should still be there. I can put it like this and put it like that. Thank you for noticing. And the half just disappeared here too. That's probably why it disappeared in the derivative. And then, in the end, and this will need we can replace the y with what we had originally. Do you want to do this one the other way as well? Just for fun? I'll let you write that down. And you can decide which method you like better. Right, so this is the new method where you take the natural log of both sides and use your log laws to get rid of quotient rules, product rules, and extra chain rules. If we did this one the old way, y prime would equal. It's a quotient rule. So I keep the bottom the same, multiply by the derivative of the top. Ooh, the top is a product rule. So I'm going to put a big bracket. How do I do a product rule derivative? I keep the first one the same, multiply by the derivative of the second one, plus keep the second one the same, multiply by the derivative of the first one, and the derivative of the first one has a chain rule, so the chain rule would say do the outside function, keep the inside the same, multiply by the derivative of the inside function. At this point you're probably lost where you were, so start all over again and say, I was doing a quotient rule. Quotient rule means, oh yeah, I kept the bottom the same, I did the derivative of the top, now I have to subtract, keep the top the same. Multiply by the derivative of the bottom. And the bottom is a chain rule. So I would have to do my outside function, the half would come out in front, to the minus a half, multiplied by the derivative of the inside 3. And now I forgot where I was, so I start all over again. I was doing quotient rule. Quotient rule means keep the bottom the same, derivative of the top, subtract, kept the top the same, derivative of the bottom over the bottom squared. And if I square that square root, it'll just be 3x minus 1. I don't know. The other one had more lines of work. But this one you have a better chance of getting lost along the way. But I find on the ones where you have a good chance of being lost along the way, whenever you're like, I think I might be lost, notice how I went back to the beginning and just talked through where I was. And you don't get lost on the second talking through because you're like, oh yeah, I kept the bottom the same. I did the derivative of the top. Even though it's a big complicated thing, I don't have to worry about that right now. And then minus kept the top the same, derivative of the bottom over the bottom square. If you went and took this and noticed here, this was your original function, you technically could factor that out. If you factored it out, you would get exactly this form of the other one. So they're equivalent, but they look a little bit different. In a multiple choice, if you do it one way and it doesn't look like any of the multiple choice answers, you might want to try the logarithmic way to see if that gives you an answer that matches up. But there are some questions that we don't know how to do with any of our laws. Here's a great one. You have y equals x to the x. This isn't a law that we have. Like you could do 2 to the x, 3 to the x, e to the x, a number to the x, but you never could do x to the x. So what we do is we take the natural log of both sides. This allows us to bring that x out in front. And now we can do implicit differentiation. Take the derivative with respect to x of everything. Do you see on the right you have a product rule? So on the left you'll just get 1 over y dy dx. But on the right we keep the first the same, derivative of the second, plus keep the second the same, derivative of the first. The x over x simplifies just to be 1. And so dy dx will equal x to the x, 1 plus the natural log of x. Here's another way you could do this with natural logs. I like the logarithmic better. You know how this works, right? Like if you have e to a natural log, those are inverses of each other, they'll cancel each other out. If you have 2 to a log 2, those are inverses of each other, that would cancel out. Because one undoes the other one, leaving you just with the number. So I could write x to the x as e to the natural log of x to the x, because these would cancel out, that still would be x to the x. But then I can use a log law up there to write this as e to the x natural log of x. Then if I did the derivative, it would be a chain rule. What's the derivative of e to the x natural log of x? That's e to the x natural log of x. That's the outside function. Multiply the derivative of the inside would be a product rule. Keep the first the same, multiply by the derivative of the second, then keep the second the same, multiply by the derivative of the first. You could substitute back, because e x to the natural log of x is just x to the x. And you could substitute back to get the same answer. So the idea of logarithmic differentiation is that if you have x to the x or any version of that, we don't have a log law, or we don't have any derivative laws for that. Then you'd have to take the natural log of both sides and use logarithmic differentiation. If you have a really complicated product quotient law one, taking the log of both sides could simplify to make it easier, but as we saw with that last one, you could still do it with your old methods. So here we have an x to the x with extra things happening. So you would have to use logarithmic differentiation. I like this left-hand side better, where you take the log of both sides. That allows you to bring that exponent out in front. Oops, cheated. Then you can take the derivative of both sides. On the right-hand side will be a product rule. So keep the first the same, multiply by the derivative of the second. Keep the second the same, multiply by the derivative of the first. Multiply both sides by y to get dy dx by itself, and then in the end you can substitute back in, so your answer is in terms of x only. course, if you wanted to, you could use that other technique as well. Change it e to the natural log, which brings it out in front. Both of these things technically mean the same thing. But this is the way that you can represent the number e as a limit. And it's kind of counterintuitive and kind of interesting at the same time. It's counterintuitive because as h goes to 0, what's going to be inside the brackets? 1. Same thing as n goes to infinity, this 1 over n would be 0, and you get 1 inside the brackets. And 1 to any power, you should think should be 1. And yet it's not in this case. As you get bigger and bigger and bigger numbers, okay, this gets closer and closer to e. In fact, if we take our graphing calculator out, I'm going to go to y equals, clear out these, bracket, 1 plus 1 over x, bracket to the power of x. So the idea is, as I get bigger and bigger and bigger, this looks intuitively, I think if x is 1,000,000, the inside is 1. 1 to any power should be 1. I think it's 1. But it actually, if we look at a table of values, we get higher and higher. They seem to keep increasing. And it's getting closer and closer to 2.7, which is E. The formal proofs are in your textbook. Check them out, page 257. Express each number in terms of the number e. So we know that the limit of 1 plus h to 1 over h, as h goes to 0, is e. Question is, what does that 2 do to our equation? And so we get a little creative. We try to make it look like this. And to look like this, you have an h inside and a 1 over h there. So I have a 2h inside, so I get a 1 over 2h in the top. And in order to get that 1 over 2h, I'd have to square it to cancel it out. So this becomes the same thing as a limit as h goes to 0 of 1 plus 2h to the 1 over 2h. And I could say temporarily, I'm going to let k equal to h. And does it make sense that as h would go to 0, so would k? This allows me to rewrite this as a limit as k goes to 0 of 1 plus k of 1 over k. This inside part is e, so by adding that 2 inside, it's going to get closer and closer to e squared. We haven't done limits for a while. Remember your limit properties? That you can do the limit of the inside and then square it afterwards? So same idea here. We know that if we had 1 plus 1 over n to the n, that would equal e. So I need to get this to match up with that. First of all, I can always put something on the outside. But what I want, and maybe you think of it this way, because this is a 1 over n. That 3 on the top, I can move to the bottom of my fraction by making it n over 3. Does that make sense? A couple of ways you can think of it. What would I need to multiply the top of this fraction of 3 by to get it to be 1? I'd have to multiply it by 1/3. If I multiply the top by a fraction by 1/3, I'd have to multiply the bottom fraction by 1/3. Do you see that that would give you an n over 3? In order for it to match up with this, I would need an n over 3 there. Agreed? But what do I have? I have a 2n instead. If I wanted it to be a 2n, there would need to be a 2/3. No, sorry, not a 2/3, just a, wow. If I wanted this to be a 2n, I'd have to have a 6 out there. Because 6 times n over 3 would be 2n. And so now this, I like it better when it matches up. This and this are identical. And then I let my k equal the n over 3. As n goes to infinity, k would go to infinity. And this is equal to e to the 6. Yes.
Why are we trying to express e as limit? Are we going to use this, or is this just?
It's where e comes from. Okay? And yes, we do use it later on, but it also comes up in like these limit questions. And it's sort of, in calculus, when you get a calculus book, there's sort of two views of teaching calculus. Okay? Most calculus books will say early transcendentals. E is called a transcendental number. And early transcendental calculus teaches you the derivative of e to the x early. The derivative of e to the x is e to the x. Can you prove it? Unfortunately, you can't prove it early. Because you would have the limit as h goes to 0 of e to the x plus h minus e to the x over h. You have a problem. You have a problem trying to figure this out early on. Okay? Limit as h goes to 0. This is e to the x times e to the h. So what I could do is I could factor out the e to the x on the top, and I would have e to the h minus 1 over h. And try to figure out how I can go about manipulating this to get this form of the equation. But it's not easy to do. And that's why some textbooks say early transcendentals. They technically mean we're teaching you calculus, but we're theoretically cheating. Theoretically, because you can't actually know how to do this yet without doing something more complicated and then taking that complicated thing and coming back to the beginning and now adding e. And we could do it that way, but for most of you, you're not actually going through the calculus as we're going at the same time and being like, I theoretically need to prove everything. We didn't prove the product rule. We didn't prove the quotient rule with the definition of the derivative. We've done a lot of derivatives that we didn't do with the definition of the derivative because it would be way too complicated and get us stuck. So we're doing calculus, we're knowing how to use it. Technically, we're cheating sometimes because we're using rules we're not allowed to use yet. A purist would say, oh, you can't use that yet, you haven't proved it. And historically, that would have all had to have been proven eventually in order to be able to use it. But now, purpose for you in this class is to be able to learn calculus and use it. So it makes sense to teach some of those things early on.